Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. A couple of lectures ago, we looked at voltage-controlled oscillators that generate sawtooth waveforms. And today we're going to look at oscillators that create triangle waveforms. As our primary example, we will tackle the Buchla 259 complex waveform generator. What I'm showing here is actually a reproduction of the front panel because this was the cleanest image I could find. Notice it does not have the Buchla Associates, Berkeley, California at the bottom here, which is the right way to do a reproduction. Don Buchla himself passed away a few years ago, but the Buchla company has continued through various ups and downs and through various guises. And even if you reproduce one of these front panels for your own use, you may pass away at some point, and then somebody will find a front panel you've made in the attic, and you wouldn't want someone to unknowingly sell it as a Buchla original when it's really not. As a bit of a review, remember that we looked at a sawtooth generating oscillator that in our analysis here took a constant and then integrated it, although I am crossing abstraction barriers a bit here by using the letter I because we are going to eventually represent that as a current. But for right now, I want to think about things at a more abstract level than the electrical circuit level. Anyway, assuming that this is constant, as long as we're integrating it, the output is going to go up. And what we do is we set up a comparator, compare that output of the integrator to a threshold, and when we hit a certain threshold, we create a reset pulse that tells the integrator to reset back to 0. Now, we have looked at circuits that will take a sawtooth wave, rectify it, and then shift and scale it, and turn that into a triangle wave. But suppose we wanted to just natively generate a triangle wave. Well, we can use the same integration idea, but what we do is we flip what constant we're putting into it. So switching back and forth between this number and a negative version of the number, we could have a triangle wave that goes up and down. And in this structure, we don't need a reset coming into the side here, because what we're going to do is we're going to take the output and run it through a comparator, but what we're comparing it against isn't a fixed threshold. It's a square wave that's basically, in a logical sense, the output of a comparator. Of course, when we implement this as an electric circuit, we'll probably need some sort of different scalings and shiftings because we want to have a value compared against here, and we have some sort of logical information represented as a voltage here, and we may need some other parts to make that work. But the general idea is that we'll actually get two waveforms out of this. If the output of the integrator is smaller than this upper threshold of the square wave, then the comparator is outputting sort of a logical true, which in this case we'll say picks this input with the positive constant. But once it exceeds that threshold, the output here sort of turns into a logical false. And then now what we're going to be comparing to will be this lower threshold. And the logical information that we're feeding to the switch picks this negative constant. So we'll now start to drop until we hit the point where we exceed this lower threshold, and then everything switches back over again, and then we start climbing. So we naturally get two waveforms out of this. We get a triangle wave and a square wave. Now, that square wave has a 50% duty cycle. If you would like a rectangular wave with a 25% duty cycle or whatever, you can take the sawtooth to rectangle wave shaper circuit, which was basically just a comparator that we looked at last time, and just run this triangle through it instead of a sawtooth, and you can still get a nice generic rectangle output that you can apply pulse width modulation to. But in any case, it is nice that we can just get a square wave out without much extra work at all. Now, you might have looked at the sawtooth core and thought, hey, we get another waveform out here. We get this nice impulse train. But these pulses are too quick to actually get a meaningful audio waveform out of it, whereas the square wave from the triangle core is in fact useful. Okay, now fasten your seatbelts. What I'm showing here is the main core of the Buchla 259 principal oscillator. First of all, don't panic. We'll simplify this fairly quickly. Now, reading a Buchla schematic is a uniquely surreal experience. You won't see other kinds of schematics like them. They really seem to have come from another dimension. So I've taken the main parts of the 259 principal oscillator that I want to talk about, and rendered them here. There's a second oscillator on the 259, the modulation oscillator, but there's really just this subset that I want to focus on for now. To allow you to reference things on the original schematic, I've put down the various numbers that Buchla used. That's just for reference, so the next step I'm going to take is just to drop those designations and leave in the component values. So the main structure we have here is that we have an op-amp with a capacitor that we use to form the integrator. This is the same as what we saw with the Sawtooth core. Now for the Sawtooth core, I didn't have any of this stuff over here, and I just had the I-frequency current generator over here. For this triangle oscillator, I need to have a bunch of complicated things in between, and there's a couple ways to think about this. You can think about this set of 4 BJTs as a primitive OTA, operational transconductance amplifier, that we're running way out into the saturation mode. Or you can think about this differential pair here as basically being a couple of switches that select a couple of options. If this BJT is switched on and this BJT is switched off, we have current being pulled out of the capacitor. Whereas if this BJT is off and this BJT is on, we have the same current, but it's going through this current mirror. So there the current is being shoved into the capacitor. Basically, the square wave has the effect of switching which of these transistors is on and which is off back and forth. Over here, we have an LM311, like in the electrode notes design from Hal Chamberlain's book for the Sawtooth oscillator. That, being a comparator, is obviously doing the duties of the comparator. So, to tackle the circuit, let's pick a few spots that are easy to analyze, namely the ones that are just setting DC bias points. So, I see that there's a 15K voltage that's being split over two 100K resistors. The capacitor here is just playing the role of filtering out glitches. It's not terribly important from analyzing the logic of the circuit. So, basically, this is just taking that 15 volts, splitting it into 7.5 volts, and so we're setting a 7.5 volt bias. And of course, part of the analysis here is that we've assumed the TL082 is ideal, so there's no current being drawn into the positive input, and we could just use this voltage divider. Also, part of assuming that the TL082 is ideal is that the output here will create whatever current and voltages are necessary to set the negative terminal at a 7.5 voltage as well. So basically, this is setting a DC bias point that you basically need to have this part of the circuit compatible with the rest of the transistor structure over here. The transistors forming the current mirror aren't magical. If I have 15 volts up here, I couldn't have something like 17 volts down here. I have to have sensible voltages going down through the chain here. And the same thing is true once we actually get into the details of the exponential voltage source. And admittedly, I keep putting off talking about these exponential current sources for later lectures. But we will get to them, I promise. Okay, so let's look at the 15 volts being split down the 100K resistor and the 22K resistor on the left. I'm going to assume that this transistor has a pretty big beta, and beta is sort of an imaginary parameter, but it's kind of useful. Anyway, I'm going to assume that the current flowing through the base is negligible, and that's an assumption I'll always make in this class. In a class like ECE4450 Analog Electronics, I generally would not make that assumption off the bat. Anyway, because we're assuming that the current flowing through the base is negligible, I can again just use a basic voltage divider. So 15 times 22K over 122K gives me 2.7 volts. So I'm just going to replace that resistor divider with 2.7 volts. All right, so let's tackle the rest of the circuit. So let's take a look at the positive input of the 311. The square wave output of the 311 comes back to the positive input through a simple one-pole low-pass filter created by this 10K and 220 picofarad capacitor. If I compute the cutoff frequency associated with that low-pass filter, I get 72.3 kilohertz. So this is telling me that it's basically there to filter out glitches, and so I'm just going to ignore it. So let's just pretend that the square wave goes to the 311, and the 311 is perfect. And part of assuming that it's perfect is that we're assuming that the input impedances are infinite, so there's no current flowing through here. Okay, so let's redraw the schematic with that approximation of taking out that RC filter and focus on the output of the comparator. Remember that the 311 has an open collector output. So if the output of the 311 is a logical false, it attaches the output to ground. But if it's a logical true, then it basically disconnects the output of the 311 altogether, and we're left with whatever voltage we get from the pull up, pull down, whatever you want to call it, network out here. So what about this sync input? So this is something that you can also do with Sawtooth oscillators. We didn't talk about it during the Sawtooth lecture, but you can play these kinds of sync games with Sawtooths as well. The idea here is that you might have some other oscillator that you want to use to force various direction changes or resets of the oscillator. This is an advanced feature that I don't really want to get into now. So what we're going to do is just suppose that the sync input is ground. So with that assumption, we can take that 4.99K and 24K resistor, take their parallel combination, and replace it with a 4.1311K resistor. And yes, I'm being a little ridiculous with these significant digits. So with that in mind, we can now see what voltage we get for the square wave output when the result of the 311 comparison is a logical true. And that would be what we would get from a basic voltage divider, which here is 4.39 volts. So if the voltage at the positive terminal is bigger than the voltage at the negative terminal, we get 4.39 volts in our square wave. Otherwise, we get 0 volts because the output here is shorted to ground by the 311. Now, if you look on the actual schematic for the Buchla 259, Buchla wrote 4.29, so close enough for rock and roll. So, as I mentioned earlier, you can think about this set of 4 transistors as a primitive OTA. Now, if you look at a filter chip like the SSM2040, you will find that the OTAs in that chip most likely consist of these 4 transistors. But the IC OTAs we've looked at so far, like the LM13700 and the CA3080, those generally have some more stuff. There's usually another current mirror here and another current mirror here that sort of buffer the current output. And you can imagine incorporating those by switching which of the inputs you consider positive and which you consider negative, or equivalently swapping the direction of the current output. Also, those fancier OTAs typically had a current mirror down here at the current bias input. So things like the 3080 and the 13700 have a current that flows into the OTA, but the simple one we've drawn here has a current flowing out of the OTA. So in this case, let's think about the current flowing out of the capacitor in the integrator loop as being I subscript SW with the current arrow pointing left. Now, if you think back to that lecture about OTAs, remember OTAs have a hyperbolic tangent nonlinearity. The VT you see in the denominator here is usually considered to be 25 or 26 millivolts. That varies with temperature, but it doesn't really matter here because when we plug in the values that we have for our square wave output, namely 4.39 volts or 0 volts, well, once we subtract out the 2.7, and get a number and punch the hyperbolic tangent button on our calculators, you wind up with something that's either 1 or -1. So the current here that I've called I switch for switch current is basically either I freak or minus I freak. And as I mentioned earlier, you don't have to really interpret this as an OTA. You can just think about these transistors here as not being a complicated differential pair like in an OTA, but as just being a set of transistors where either one is off and the other is on, in which case we have a current flowing out of the capacitor, or we have a situation where this transistor is on and this one is off, in which case it flows through the current mirror and that swaps the direction. So usually if you're building an OTA for linear computation purposes, like in a filter, you would like the NPN transistors here to be matched. Since we're just using these as switches, it's not important here that the NPN transistors be matched, but it is important that the PNP transistors forming the current mirror be matched, either in this switching circuit or in an OTA you're using for linear purposes. So you'll typically select a matched pair of transistors for this PNP, and these are transistors that not only have matched characteristics in general, but are also hopefully on the same die, so they stay at the same temperature. And if they're not on the same die, then you at least have selected two discrete transistors with similar characteristics that you've smushed together with some heatsink compound to make sure they stay at the same temperature. And the network up here with this 4.99K resistors going to the 15 volts and with this 20K pot here, this is designed to be able to trim out some imperfections in the matching. And we're talking about very, very subtle effects here because this resistor here connects that wiper of the potentiometer to ground through a 10 mega ohm resistor. So basically what you wind up doing when you build this is that you may get a lopsided triangle, and you would turn this pot back and forth to try to get a symmetric triangle. And although I didn't explicitly label it here, it would not surprise you to know that these 4.99 resistors are 1% resistors. Oh, something that I should mention, I'm using this convention of using the unit, like K, to replace the decimal point. So that keeps the notation compact. And also means that if somebody is somehow, for some reason, reading a photocopy of these slides, if a decimal point gets lost in that copying process, somebody doesn't suddenly think it's a 499 ohm or 499K resistor. It's 4.99K. Before moving on, I want to talk about something that feels a little awkward with the 7.5 volt bias here that's set by the feedback operation of the op-amp. It might lead you to think that the triangle wave itself needs to be centered around 7.5 volts, but not really. If you think about the equation that governs the dynamics of the capacitor, that's usually written as a differential equation. When you integrate both sides of that equation, there's a constant that shows up, and that constant can basically just be whatever. So the net effect is that we wind up thinking about this capacitor in terms of its dynamic operation when we're shoving a current into the cap or pulling a current out, and then it's responding by changing the voltage over here accordingly. But thinking about it in a quiescent state, we can think about this capacitor as being a DC block. So our triangle over here can sort of happily exist in a different DC universe than the 7.5 volts over here. As far as the operation of the capacitor and the op-amp goes in terms of determining V tri, all it really cares about is what's happening with the current. So the final bit of the circuitry we need to tackle is this set of resistors here. Notice that we're not taking the triangle and jamming it right into the negative input of the comparator, which I think is what we did with the Sawtooth oscillator. So we have this 15 volts through this 28.7K resistor that then connects to the triangle output through this 4.99K resistor. So that basically sets up a scaling and shifting operation. So what we're interested in is finding out what values of V tri result in the comparator deciding to change directions. And to figure that out, we have to figure out how the voltages of the square wave, as we would consider them here at the negative terminal, map back to the voltages of the triangle waveform. So basically, what voltage for V tri corresponds to a voltage of 4.39 at the negative terminal, and what voltage of V tri corresponds to a voltage of 0 at the negative terminal. So we can easily develop a relationship between V tri and V minus, the way I've called it here, using superposition. So to get this term, we can briefly imagine grounding the plus 15 volt, and that would result in a voltage divider where we're dividing V tri across 28.7K. And then to get this term, we can take this V tri node and ground it, and then imagine taking this 15 volts and dividing it across this 4.99K resistor. And then just doing a bit of algebra and rearranging the terms, we get this relationship between V tri and V minus here. And now we can try plugging in the extremes. So if we plug in 0 volts, we can see that 0 volts at the input of the LM311 corresponds to minus 2.608 volts. And if we plug in the other extreme, 4.39 volts, we see that corresponds to a V-try of 2.5454 volts, again being a little overzealous with significant digits. But basically one of these voltages is really close to the negative of the other. So if we average these, we see that we get a triangle wave out-centered at minus 0.03 something something volts, and the peak-to-peak voltage is 5.15 something something something. And so if we think about how far off that DC value is, if we take the DC value and divide it by the peak-to-peak, we get 0.61%. So basically, we could treat this as a 5-volt signal centered around DC. Now, if you wanted to go back here and change that 3 to a 2 to match what Buchla wrote on his schematics, you could rework all of these various numbers, but you would more or less come to the same conclusion. So the last thing we need to think about is how the control current relates to the frequency of the triangle wave we get out. So this is basically the same formula we had for the Sawtooth wave, but with one very important difference. With the Sawtooth wave, the time it took to travel from one extreme to the other of the output voltage correspond to the period T0. However, for the triangle wave, we have to go all the way one direction and then all the way the other direction. So really, the time it takes to transverse from one extreme to the other, that's really only half of the period. So that's why I have this divided by 2 sitting here. So if we rearrange this expression to see how the period relates to the control current in terms of the peak-to-peak voltage and the capacitance, we see there is a factor of 2 here that we did not have in the Sawtooth case. And then inverting both sides of the expression, we can get an expression that gives us the frequency. And just as a sanity check, let's think of the influence of the various factors. If we put in more current, we're traversing that peak-to-peak to swing faster, so the period is shorter and the frequency is higher, which makes sense. All other things being equal, if we make the peak-to-peak voltage range that we need to traverse larger, it takes us longer to transverse that range, and hence the period is longer, and so the frequency is lower. And all other things being equal, if we increase the capacitance, it means that we need to shove more current into the capacitor in order to get an equivalent voltage change that will also lengthen the period and give us a lower frequency. So thinking through the effect of these various variables gives you a way of coming up with this expression without necessarily memorizing it. Just remember the Sawtooth version did not have the 2 here, but the triangle version does have the 2 here. And if we rearrange this formula in terms of what current we need in order to achieve a certain frequency, again, not forgetting to include the 2 here for the triangle case, and plug in the values for the peak-to-peak voltage and the capacitance that we had earlier. And let's say we are wondering what kind of current we need to get the frequency associated with middle C on the piano. If we don't forget to multiply by 2 here, we wind up with 12.674 microamps. So again, we're talking about tiny, tiny currents.